project. So we will start with the first presentation from Dr. Yu Jin. Dr. Yu Jin obtained his Ph.D. from Universität Berlin and was currently as an associate researcher at Shenzhen Institute of Information Technology. He is a member of German Chemical Society Construction Chemistry branch and reviewer for some prestigious journals like Journal of the American Ceramic Society, etc. He has published 19 journal papers, including those in Cement and Concrete Research, Journal of Cleaner Production. His research interests cover the utilization of solid waste alkali activated material, latex modified cement-based material. So we will have about 30 minutes for each presentation, question included. So please, you can start.
Hello everyone, can everyone hear me?
Yeah, very well.
Okay, good. So also my presentation, right?
Yes. Yeah.
Okay, good. Today, my topic is about on the reactivity mechanism of supplementary cementitious materials by alkali activation. Actually, supplementary cementitious materials is not very new in concrete technology, but its reactivity mechanism is by so far is not just well understood. So my study is on the mechanism of this SCM. So this presentation will be delivered in these 4 sections. First, I will introduce the background and the method I use in my research and some results, and followed by conclusions. So in the first part, I will shortly give the background about the use of SCM. As we all know, cement production produces or generates quite a lot of CO2. In addition, not only just the environmental impact, but also the natural resource consumption. For example, this is the data in 2017 in China. The cement product clinker was produced 1,003,76 tons. It's a huge amount, and it consumed about 1.8 billion tons calcite and 340 million tons clay and also the coal. So in this sense, we cannot continue with such a high natural resource consumptions. In this way, many industrial and urban solid waste will be added in the cement production, such as blast furnace slag and fly ash and so on. In this research, I will just focus on this blast furnace slag and fly ash because they show some similarities. For the blast furnace slag is a byproduct from steel making, and the molten slag will be water quenched and grounded into powder. So this is what we saw, and we in this presentation I will just call it slag for short. And coal fly ash also is a byproduct from coal combustion, and this organic matters was burned out, and the minerals was transformed from a glassy state or some other crystals and a very high temperature. This very complicated process made the coal fly ash is its microstructure very complicated. So for this as this kind of SCMs like blast furnace slag and also fly ash, they show basic similarities. The most reactive component of these two SCMs are the glass phase or the glass component for slag is more than 90 or 95% is component is glassy phases, but for flash it ranges from for example 50% to 90%. It depends on the mineral on the coal mineral, or also depends on the heating history. So in general, they share a kind of glass structure in this way. The glass is made of so-called network former. It's the tetrahedron of inner silicon tetroxide or aluminum tetroxide. And it also, this connected network is also modified by those so-called network modifier, or in other words, alkali cations, like calcium, sodium, or potassium, and these alkali cations will break down the connected network and increase the reactivity of the SCMs. This is a very important concept in glass chemistry, that the non-bridging oxygen, those I think in orange color, and this non-bridging oxygen coordinated with the alkali cations, they will give the SCM high reactivity, and this non-bridging oxygen per tetrahedron is used as an index to evaluate the reactivity of SCM. Recent studies give some examples. Because the aluminosilicate glass dissolution, we all know this aluminosilicate dissolved and high pH, and this is just a general idea how it dissolved in high pH solutions. First, the cations exchange with the potassium with the hydrogen in the aqueous phase, and the water or hydroxide will attack the silicon oxide, aluminosilicon oxide silicon bonding, and this silicon silicate or aluminate hydrate will released from the glass and into the alkaline solution, and the solution that will be controlled further by the dissolution precipitation process and formed hydrates. This is just a general steps for the glass dissolution high pH, and these glass structures has shown it's or we say this MBO per tetrahedron, MBO per T. This parameter can be used as an index to indicate the reactivity. For example, the dissolution of the silicon in the alkaline solution, or the glass reacted, and also the heat released. All these parameters can be correlated with this MBO per T parameter. So this is well used to quantify or quantitatively determine the reactivity of SCM. Also, it not only just used in the Pew system, but also this SCM, for example, the flash blended with cement also shows this the power of these parameters. This network ratio is just another name of the MBO per T, and this MBO per T gives a very good correlation between this ratio and the heat release, in other words, the reactivity of the fly ashes, no matter the glass content and or other chemical composition, just related to these parameters. So in this, in my research, I would like to further explore some questions left. For example, the first one is, we know the glass structure of slag and flash in general, but what's the difference? And the correlation between the glass structure and the reactivity is, it can be exactly defined by this MBO per T parameter, or there's something else. And also the reactivity under various alkali conditions, because we know it's a solution controlled process for the hydration of SCM. So this project, this research will go on these three aspects. I will just skip the introduction of the chemical composition, but in general, there are very typical chemical composition for slag and fly ashes. And the particle size for the slag, it's the D50 particle size is around 10 to 20 micrometer, quite typical. And for fly ashes, the particle size is more coarse, it's around more than 30 or 50 micrometer in D50. And also I use different alkaline solution to activate the SCMs. For this pure system, it's more easy to explore its mechanism and use the slag water slag ratio and water fly ash ratio in 0.45 and 0.4. For the characterization method, firstly, I use the quantitative X-ray diffraction to determine the glass content in the flash, and also quantitatively determine the glass phase and also the crystal phases. And I also use the solid state nuclear magnetic resonance. So use this kind of method, we could, for example, determine the atomic state of silicon and aluminum. In this illustrated schematic illustration, we could see that for different chemical shift, we can know the different stage of the silicon, and also for aluminum atoms, the different chemical shift can give the information of its coordination state. For example, around 80 to 40, aluminum is tetrahedrally coordinated, and around 0 to 20 is 6 coordinated. In this research, I also use the energy dispersive X-ray spectroscopy to determine the chemical or elemental mapping or elemental distribution in the alkali activated materials, and use this method, and in coupled with some image processing, we can determine the degree of hydration of this. For example, slags in this case. For its reactivity, we all know that the isothermal calorimetry is a good method, and it can be used to indicate the reactivity, and especially in the reaction kinetics. And in this study, I use the cumulative heat as an index to evaluate the reactivity of SCM and given time duration. Now I will go to my results. The first results is about the spatial distribution of main elements in the slags, and therefore from the production of the slag, we know it's in a molten state, and this molten state can be regarded as a homogeneous state. And from our results, either from the X-ray fluorescence gives the chemical composition of the slag in general, or from the EDX sports, so the chemical composition of individual small scale was determined. Compared with these two methods, we can find this both methods gives very similar results. So it means that chemical or the main elements distribution is quite homogeneous in slags. Further, we in the background section, we introduced the glass structure of SCM, and for this kind of glass structure, actually we can further determine its connection state by a model. I will not give full detail in this presentation, but if you are interested in its model, you can refer to my publication in CCR, which was published in 2019. And in this model, we could see the differences of these two slags. For the slag S1, it shows a very depolymerized degree. It means that there are a lot of monosilicate, and it can be easily released during by the alkali activation. And for the slag S2, its its polymerized state is much more complicated. It means that it's also its dissolution and release into the alkaline in the solution is more complicated than S1. And the other SEM is the flash, and the flash shows the major crystalline phase are quartz and mullite, but it's mullite is just a general description. For different flashes, it has different chemical compositions and also structures, and also the glass content of these flashes range from 56 to about 85%, and from this glass chemical composition, it can be seen that it constitutes mainly from silicon and aluminum with a small amount of calcium and magnesium and other alkali cations. For the spatial distribution of these main elements in the flashes, it's totally heterogeneous, and chemical elements distributed were distributed in this slag spheres is quite, it has no homogeneous structure. It's totally heterogeneous. And from its aluminum and silicon stage in the glassy phase, it also by some curve fitting method using a well-defined model, and we can see for the flashes, the major aluminum coordination status for tetrahedral coordination, and just small amount of this flash is sorry, I made some wrong mark. It's 6 coordinated, and from the ratio between the alkali cations and aluminum and iron contents, we could also speculate in the aluminum 4 coordinated aluminum proportion in the glass structure. Also from the silicon stage, we could see in the silicon from mullite and also in the silicon from tactile silicate, either from the crystalline phase like quartz or from the glassy phase. Based on these chemical environments, we could give a model to describe the glass structure of this flash. It can be simply ascribed as 3 different part glasses. And the first part is the per-alkaline aluminosilicate glass. The structure is similar with that in slag. And the second, this is the most reactive part of the flash glassy phase. The second glassy phase is the so-called aluminosilicate. The aluminum is 5 or 6 coordinated because it's lack of cations in these structures, and this reactivity is weaker than alkaline aluminosilicate. And the third kind of glass structure is quartz-like glass structure. And for this pattern, the reactivity is quite low. And for the reactivity, we also use the so-called non-bridging oxygen per tetrahedral parameter to indicate its reactivity. but different from what described previously, we including the sodium and also the silicon from the activator. We call this as a pseudo or non-bridging oxygen per tetrahedron parameter. And use this parameter, we correlate this parameter with the cumulative heat in under 24 hours or after 72 hours, and we could find a very linear correlation between these parameters and the heat released. Unfortunately, if in the presence of the silicate, the correlation is not such good. It means that in the presence of the silicate, the reactivity of this SCM is not only controlled or not only dominated by the dissolution of the glass, but also by the reaction products which impeded or influence the reaction of the SCMs. This not only applies this pseudo non-bridging oxygen per tetrahedron parameter is not only applied to slag, but it also applies to fly ashes. Only for some fly ashes with very high iron content, it doesn't follow these parameters, but for the other fly ashes, it can be seen that it's clearly these parameters correlated well with the cumulative heat. And in other words, for kind of fly ashes, it makes no sense to increase the alkalinity since its reactivity is quite low. It cannot be enhanced by the only alkaline solutions. For this kind of fly ashes, it's suggested to use, for example, elevated temperatures to increase its reactivity. In this section, I will give just the alkali activation mechanism of slag, because as introduced before, slag is much more simple than that of fly ash. So this part is only slag is discussed in this part. Firstly, I look at the degree of hydration of these alkali activated slags in different activation conditions using different alkali concentration and also the silicate concentrations. It's denoted as two numbers. And this first number is the weight percent or the concentration of the alkali concentration. The second number denotes the silicate modulus. For 0, it means that there's no silicate from the activator. And from this DOH analysis, we found there's no clear trend, but in general, with the increase of the silicate concentration, the degree of hydration of the slags decreased, and for the difference between these two slags is not very obviously to observed. If we presented the degree of hydration against the pseudo non-bridging oxygen per tetrahedron parameter, we could see it correlates well with the alkali activated slag made of S1, but it's not so good with that made of slag S2. And if we plot this degree of hydration against the cumulative heat, it shows a relatively good correlation, and it means this degree of hydration makes sense since it correlates well with the cumulative heat. but our parameters used to describe the degree of hydration, it works not very well. It again indicate that in the presence of the silicate activator, it will influence the degree of hydration in not just the dissolution, but also the reaction products. In this ADX mapping method, we also found some phenomenon that some slag particles show silicon-rich. We call it silicon-rich slag particle. And this silicon-rich slag particle, the volume percentage of this silicon-rich slag particle is correlated with the alkali activation condition. Generally, with the increase of the silicate concentration, the decrease of this volume percentage of silicon-rich slag particle. It's reasonable because if the solution is saturated with the silicate anions, the dissolution of the silicate from the glass phase will be inhibited. And we also found a very distinct difference between the silicon-rich slag particles, the volume percentage of this silicon-rich slag particles between these two slags. So for slag S2, it always shows a higher volume percentage. And this is in enlarged image. You could see that quite a lot of silicon species deposits on top or on the surface of the slag particles. We further examine second electron images to see what's the details of these particles, to see if there are visible hydration products or not. And from this high resolution images, we cannot really observe some reaction products. Instead, we see some very typical HPs, which means the dissolution of the dissolution of the glass phase. Actually, for this glass reaction in aqueous solution, there are two models. And the first, one model is is so-called leach layer model. I will not introduce it here. The other one is the so-called precipitation dissolution reprecipitation model. Within this model, the reaction front went on and glass dissolved and precipitate new phase, and then interfacial fluid went on to interact with the glass surface, and reaction front went on. This dissolution precipitation mechanism can explain why the silicon-rich particle phenomenon, because if the leach layer model dominates, it will not has such silicon-rich particles. For the alkali activated slag, this reaction can be simply expressed in this schematic illustration, and these two major hydration products is so-called cash gel and hydrocalcite. And these two hydration products may have indicates how the alkali conditions influence the reactivity of the slag. By employing the ADX methods, we could determine the chemical composition of the pastes, and from the this plot is magnesium silicon ratio against aluminosilicon ratio. And from this plot, we could speculate the magnesium alumina ratio and the slope in hydroxide. And also we can indicate the aluminosilicon ratio in cache gel. And this is the results. Normally, the magnesium alumina ratio in hydroxide ranges from 2 to 5, but our results shows that the magnesium alumina ratio is most of the magnesium alumina ratio is below 2. The alumina silicon ratio we determined is mostly above 0.19, and actually the saturated alumina silicon ratio in cache gel is limited to 0.19. So it means that what we speculated from the plot is our estimate of either underestimated the magnesium alumina ratio in hydroxide, but also overestimate the alumina silicon ratio in cache gel. These results indicate that hydroxide intermixed with the cache gel, and we cannot easily distinguish these two hydration products in hydrated pastes. We use the solid state nuclear magnetic resonance to determine the coordination state in alkali activated slag. And by the results, we could also correlate it with our proposed non-Bridgen oxygen per tetrahedron parameter. And from this plot, we could see clearly that this non-Bridgen oxygen per tetrahedron parameter can indicate the alumina, the 6 coordinated alumina ratio in the paste. And this 6 coordinated ratio in the paste, it can be further deconvoluted into different hydration phases like FM, but it's just in small amount. And also the hydroxide is the main alumina containing hydration products and so-called pseudo aluminate hydrate. And this pseudo aluminate hydrate is actually not the new hydration products. It's a misunderstanding in previously, and actually it's the 6 coordinated alumina in the cache gel structure. And from this deconvolution, we could get a ratio of hydroxide in hydrated paste. And from the result, we could see clearly that silicate concentration is determinative for the formation of the hydroxide. It's the formation of hydroxide is solely or nearly only depends on the silicate concentration. By the results obtained so far, we could propose a reaction mechanism of alkali activated slag. So it first, if in the presence of silicate anions in the activator solution, it can react immediately with the species dissolved from the SCM or here slag particles and formed cache gel and hydroxide. The formed cache gel, especially when the initial silicate concentration is very high, it will impedes the further reaction or the further dissolution of the slag particles, and in this sense, the reactivity of the slag particles is low. So for the slag, the reactivity of slag by alkali activation, the hydrolyze of alumino-oxygen-silicon bonding, or the depolymerization of the glass network is as important as the formation of the cache gel and interface. These both factors determine the reactivity of slag by alkali activation. In the end, we go to my conclusion. The glass structure in slag and flash is mainly aluminosilicate, which was modeled by different models. Depending on the content of alkali cations, for flash, thermal history plays an important role in the structure as well. Despite that, the reactivity of both slag and flash by alkali activation can be linearly correlated to the depolymerization degree of the glass structure, even for flash. And ambient temperature, if the temperature raised, this correlation may not be applied. The correlation can be also extended in alkali activation systems in the absence of silicate ions. And for SEM used, for example, in cement, and silicate concentration is very low. So the reactivity of slag and flash can be simply correlated to the depolymerization degree of their glass phases. And the depolymerization degree of the glass structure determines the fate of alumina, including the precipitation of hydroxide and the incorporation in cache gel. The hydrolysis of the alumino-oxygen-silicon bonding in the glass structure of slag is a key for the reactivity, but also the formation of cache gel in the vicinity of the slag particles determines the dissolution of the aluminosilicate glass as well. So this both factors matter with respect to the slag reactivity by alkali reaction. But in the case of cement blends for slag, its reactivity is majorly controlled by the glass dissolution of the slag. Of course, the formation of this cache gel on the surface of the slag particles will also has an effect on its continuous dissolution, and this will be researched later. Okay, this is the end of my presentation. Thank you very much for your attention.
Thank you very much, Dr. Eugene, about this very interesting